So I'm very pleased to give this talk today, and thank you organizers for inviting me. I chose to give this talk a very general title, different from what I announced at the beginning, because I also give some very general introduction to the Nernst effect in the group rates. The personal work I did on this topic was performed with my advisor and also with Sashdev. So I really start with some very general review of experimental and theoretical results, which are somehow quite historical compared to what I will tell afterwards. I will concentrate on two particular experiments which showed new details of the Nernst effect in group rates. And the first issue is that stride order in these materials has been shown to be somehow related to the Nernst effect. The question is how it is so. And this is one publication I'd like to present to you, which I personally published. And the next topic is the question how rotational symmetry breaking is related to the Nernst effect. There has been really some spectacular discovery that somehow the pseudo-gap phase seems to be related to rotational symmetry breaking in terms of the Nernst effect. And there I will also present some theoretical analysis of this question. And to start with, the Nernst effect itself is maybe not very well known to everyone. So just some basics. It's essentially a thermoelectric phenomenon that is completely analogous to the Hall effect. So you require strong magnetic fields to observe it, because usually it's very small, it's difficult to measure, and especially difficult in metals, where you see no features. It's very small, it's some microvolts usually. And so it took a long time to use it in a similar manner than the Hall effect, for instance. And the main problem where one discovered that the Nernst effect itself has a big advantage in some sense were correlated electron systems, especially the group rates, where one has really now the opinion that the Nernst effect can give new insights how this phase diagram originates. And now, pictorially, somehow how you should understand the definition of the Nernst effect. It's just an analogy to the Hall effect. You replace the longitudinal electric field by a thermal gradient, but the rest remains nearly the same. You have a strong perpendicular magnetic field and measure the transverse in-plane voltage generated by this gradient. And you do so in absence of any longitudinal current, and that's the boundary condition. And what's seen here, that is some special source of Nernst signal, namely some vortex moving along the thermal gradient. And I explain in a minute how this really can generate a Nernst effect. But that's specific to the group rates. I think this should be shown even during this conference quite a lot of times. So just briefly, what I'm interested in this group rates phase diagram, where you see electron-doped axis here, the electron-doped axis, and this are doped holes. Mostly I'm interested in this hole-doped part. And
I find that this phase diagram needs to be boycotted because of that normal outrageous.
yes, it's
a
not
strange metal or bad metal.
Yes,
mystery metal.
I personally would favor strange metal,
Okay.
but it's also not my reference, fortunately.
So
Well, I just refer to the history. It's not my history.
He's quicker than the authors over there. So.
I know it very well.
It's an experimentalist. It's an experimentalist who does not maybe care about all the details.
This was a political correct.
Yeah. Yeah.
Excuse me, continue.
Okay.
There's no pseudo gap on the other side?
Well, it's
Or is it just...
Contentious, right?
first of all, it's not very pronounced. It would have potentially covering this area. So it's even difficult to identify it as a small parameter range where you could potentially see it. And to my knowledge, also, all these features seen in this phase really are not nearly seen in a large fraction in this region. So I cannot tell much about actually. I just know essentially the nonce effect properties which I will discuss, which change very tremendously in this area, are not seen, for instance, somewhere here in this area. Maybe because there are no experiments, but
there are nonce effect by green.
But not related to
Again, there was this period that electron dot was fashionable. In the meantime, somehow it's way less interesting, and the DCs are way lower.
Yes.
And the politically correct phase diagram right now is only the right-hand side, I would say.
Yeah, you can ignore it, essentially. This, I will show some brief results for the nonce effect in this part of phase diagram.
So this anomalous nonce effect has also been observed in some organic compounds.
Oh, there's no growing list of materials.
Right,
It's got very fashionable.
to what extent this phase diagram is specific for the nonce effect? I mean, is it...
Well, my talk essentially treats only cuprate materials, and why it does so, because the nonce effect is believed to give new insights in pseudogap phase.
Right.
And in other materials you don't usually have some pronounced pseudogap phase, so
Right.
that's why I'm very specifically talking about cuprates.
Okay.
However, you should be aware that the nonce effect also shows interesting details of other materials as well, but I won't discuss much about this today. It's not enough time, unfortunately. So the big question marks are what's the origin of this phase, especially what symmetries are broken. Another question is what's hidden below this dome. Is there some quantum critical point, and especially what is the broken symmetry across this point? And I'll tend to answer some of these questions in tendency by some new insights from the nonce effect. Now, this is maybe the seminal measurement on the nonce effect in cuprates, so I really am forced to tell you this. Especially, this is whole dome material now, so you change the whole content, and you see the superconducting dome is just this one here, where you have these data points, and yeah, and now you can see the contours of constant nonce signal, which are all these dashed lines, and the magnitude of this constant signal is somehow very rapidly increasing towards the phase boundary, and this somehow tells that close to the phase boundary you have a very strong origin of a nonce signal, and it has been therefore proposed, of course, close to the phase boundary you have the fluctuating vortices, and it's believed that these vortices produce a strong signal here, and so this has been actually self-discovery as discovery of fluctuating vortices in the pseudogap phase by the nonce effect. And
Why does it have to be vortices and not just fluctuating Hooker pairs, which could be another...
yeah, let me put it like this, there are different proposals how such a signal might be explained. This has been initially proposed to be a discovery of fluctuating vortices. Yeah. I have to admit there is no consensus about what is the precise origin of
But I would say fluctuating Cooper pairs or vortices are kind of the same, right? In a day or two. And the vortices are the animals that are supposed to react strongly to the thermal gradient. And you can describe in both languages, just duality.
Yeah, this is still just a possibility to fluctuate
Right,
the amplitude of
you
the
know,
phase.
you can dream about completely other things, but when you say fluctuating superconductivity, You can always use the vortex size to express the transport.
Well, there is also as long as the Larkin correction, which is.
Yeah, but this is not of the kind. These are not these tiny little amplitude fluctuations. That won't give you this kind
Well,
of. This is
to give this justice, there's at least debate whether
There's
it's,
big time phase fluctuation.
whether it's the phase or the amplitude that fluctuates, or even if it's just.
But amplitude won't give you unit phase.
At least there are publications.
You
that
do
try
amplitude, you do phase.
It's not
You
very
think-
clear. It's fluctuating superconductivity. That's somewhat clear.
So, just a few questions. So, the Nernst effect doesn't matter which way a vortex moves. The anti-vortices and vortices move in the same direction of the field,
Well,
temperature gradient.
The essential thing is that they drift along the thermal gradient. I try to explain this in the next slide a little bit more. So that's how it works in principle. It's rather phenomenological, and clearly there's no precise microscopic theory how you can relate microscopic parameters to the Nernst
So if
signal.
you have the same number of vortices and type vortices, the Nernst will be zero for this one, right?
And you have non-zero magnetic field.
Right, it's zero field. I mean, generally you wouldn't prefer vortices over entire vortices.
Yeah, you definitely need the strong magnetic
Yeah.
So
field.
the
Nernst
previous,
effect is odd in magnetic field.
so the previous slide was a finite field.
It's all finite magnetic fields, finite thermal gradients. And let me just explain the most phenomenological idea how this signal is arising. So the derivative of the phase of these vortices is by the Josephson equation equivalent to transverse voltage, and moreover you can relate a number of vortices and its time derivative to the time derivative of the phase, and therefore you see the current of vortices naturally generates this voltage here, and you can think about the Lorentz force and you will see that the electrical field generated by this voltage has to point in this direction once the thermal gradient is pointing along this direction. That's roughly the phenomenological explanation. It's not microscopically profound, and that's how you understand in principle why the drift of these vortices gives this transverse voltage. And so for is this somehow acceptable?
I'm just trying to figure out if there's vortices there, you can control them in another way, maybe with an electric field, or put some sort of extended pinning site and see if you get flux buildup.
But it also is claim of diamagnetism.
Yeah.
Yes.
Pinning won't work, it's still really very liquid.
When there's nothing specific, it's just a vortex phase of a type 2 superconductor.
So is
It's
it
not
supposed to be
giving
slow
no.
in space, or is these field-induced vortices? So do you have,
Say that.
well, if you're talking about fluctuating superconductivity,
Yes.
it's presumably close to the Stauder space, right?
Well,
But these are field-induced vortices.
No, it's
Yeah.
not 2D.
there's nothing specific, I assume. It's just the vortex phase of the type 2 superconductor, and you can drift the vortices unless they are not pinned, but if it's a type 2 superconductor, they say they are presumably not pinned if the material is sufficiently clean. And that's just the most basic setting. There's nothing specific assumed.
Question, if you do have a dirty material, do you see the next response go down?
Well, actually, there's some picture where it's difficult. I mean, I personally,
May I remember, that's not very well known experimentation, it's also French name. That is ion beam damage, right? And this, you started out as very nice and clean 1, 2, 3. There's sort of a 90K transition, and then by ion damage, the transition temperature reduces to something like 40K. And the regime that opened up there had tremendous Nernst effect, kind of suggesting by, the historic conductivity by dirt, you sort of release this Nernst regime, which makes sense when you think about it.
well, I've been thinking about the clean limits.
Yeah. Do you know this data? I mean, it's not very well known somehow.
Let me also tell you, this is not what I will base on essentially, it's just the historical remarks which I will base on later. So this is another source of Nernst effect, and this is quite more clear to understand, also microscopically. So this is an electron doped material actually. Praseodymium there in copper oxide, I think. So here you can see two different sources of Nernst effect, where I only name this one as the important one. So when you tune the magnetic field and measure the Nernst signal, you at HC2 will certainly kill the vortex phase. And also if you're above the TC, say at 50 Kelvin, you definitely are out very far away from the superconducting dome. So in this case, the signal is very linear, proportional to the magnetic field, and that's a clear signature of a signal that's originating from drifting quasi-particle with charge plus or minus something, electrical charge. So this is, can show this by analyzing linear response relation will be proportional to magnetic field. And another source you see here, which is strongly nonlinear magnetic field, unless you are below, above HT2, you have to be above, and then it gets linear suddenly. And because you kill all the vortices, and what's left is just drifting electrons, and these produce once more such a quasi-particle Nernst signal. So I will concentrate on this linear part here, and consider only quasi-particles later on, and try to understand how the normal state quasi-particles are changed in the cuprate phase diagram by analyzing the corresponding Nernst signal. So the first thing I will considering is the stripe order. So the question is essentially how stripe order.
I mean, how do you have HC2 above TC? I mean, that implies that there's a second HC2
Well,
in the
well, it's
is this in the superconducting phase?
well.
What is the
It's,
issue?
the issue is you have two different temperatures at 3 essentially.
Yeah.
One is above TC, they don't worry about the HC2 of course,
Uh-huh.
and the other is below TC.
Okay.
60K is just below 60.
Okay.
Yeah.
I got it. I got it.
See that?
Uh, And yes, there's nothing very cool.
So is there a possibility that you have vortices above TC in that regime where you see the Nernst effect or not?
Well, this temperature range certainly not. You may see it maybe at 25 Kelvin or 22 Kelvin, something you still have fluctuating superconductivity around. You may still see something like this vortex Nernst signal, but it's presumably not as much enhanced. Once you have 25 Kelvin, it will decay. Once you have 30 Kelvin, it won't almost be visible. At 50 Kelvin, as you see here, you have only the quasi-particle signals.
But it's electron doped side, the fluctuation should be weak anyway, right?
And it's weak anyway. That's another point. It's not extremely weak. You see still quite a strong Nernst signal compared to the quasi-particle effect. But its intensity is weaker than in the whole doped cuprate, certainly. Yeah. So, next thing. Now, concentrating on the normal state Nernst effect.
So, sorry about it. If you look at the Nernst signal, so you basically get like a lot of T, say T prime above TC. And that from like pseudo gap, people talk about pseudo gap based on like heat capacity or spin gap, they talk about this T star. So what is this,
Good point. Good question.
what are those temperature related?
So it's basically not equivalent. It's quite different. So you see a pseudo-gap phase boundary at some T star where you see some linear temperature dependency. Well, this is, say, doping this temperature. So across this line you usually define to be a change from the linear resistivity and temperature to quadratic or something else at least. And the Nernst signal is usually has an onset that is much lower in temperature, which is then called T nu. So
The
this
peaks
is,
at about 1.8, right?
I think it's, yeah.
You
this
start
is-
just screaming up and
it's
Nernst
distorted
temperature
due
is
to my
really
personal
gradually sliding.
ignorance. It should be peaking at 1
Yeah, so it goes down again and T-star speeds up usually.
There's no claim that this is the correct curvature, but the temperatures can
Yeah, come on,
roughly.
the Nernst effect disappears when you go really in the dark. And T-star does not, that will only increase.
Yeah, it's much, in other words, it's much lower, this temperature. When you see the Nernst effect than the cuprate's pseudo-gap temperature.
And there's other stuff like when you make your samples more dirty, you get more Nernst effect. 214 is very good. 1, 2, 3 is a bit smaller. Yeah.
Yeah.
Right, so this is attitude of weakling physics.
By the way, can you see the side? There's always complaints that this color is usable. Anyway, I'll try to use this.
So does this mean this vortex liquid picture cannot fully explain this strange matter, between T star and T mu?
Certainly there's no clear explanation why this T mu is down below here and this T star above here.
I mean, most people would take it as evidence that T-star is not really about preformed pairs and phase fluctuations. There's now complete consensus that T-star is about repeating order.
Well, the
And
amazing
of
thing
course,
of
this
this
sort
talk,
of,
yeah.
you know, local pair physics in there. But
We will come essentially to this point, explaining why this boundary is indeed the phase boundary of some broken symmetry state, which you can even explain by the Nernst effect. We cannot explain it at the moment because we now talk only about vortex Nernst effect. I now will talk about the normal state Nernst effect. And if you analyze this, you will see that this boundary is equivalent to some onset of a Nernst signal with a specific structure.
there's a class of particle Nernst.
Yeah. And that will explain that this, try to explain that this phase boundary is essentially nematic phase boundary. And that's the point where I come to. Now let's just start with the aspect of stripe order. That is something really happening only in particular materials and also at quite low temperatures, and you will know much better where to draw this actually. It's somewhere maximally close to this 1/8 and will stop somewhere at 0.20 in specific materials at least. And there you see some ordering patterns of spin and charge. And my question will be how this affects this normal state Nernst effect. And let's make it briefly. How stripe order looks like if you, for instance, use STM. You see the charge density as being large once you see this orange these contours here. And if you zoom in, you will see suddenly at this stage that indeed the period of this is 4 in the charge sector, and this relates to a period of 8 in the spin sector, and this is particularly stable at 1/8 doping. And you see here also the oxygen and copper side, so you really have this period 4 pattern. And what's specific about this pattern, why I show it to you, it also has a peculiar feature, at least this has been proposed theoretically, that bond amplitudes between these atoms are modulated as well. It's not only the charge, which are these circles, also these bonds, and in this case they have a D-wave pattern, so X and Y direction are inequivalent, and this has been proposed to explain this particular pattern. That's one of the patterns I will be considering. Other patterns that I also will consider are possibly you can also modulate spin and charge density in this fashion. That's seen in lots of materials based on titanium strontium copper oxide. There's lots of details. The basic thing is this pattern is symmetric with respect to the atomic sides, whereas this pattern is symmetric with respect to this center of the bond. That's why it's called bond-centered and the side-centered. The essential thing you have to ask, what does this pattern do with the normal state quasi-particles? That will be of interest to me. And simply this provides a scattering wave vector, which is the wave vector of the charge and spin ordering, and with some scattering amplitude that's unfortunately can also depend on spin, which I mentioned here, that's wrong. It's depends on spin if it's spin stripe order. If it's charge, you just have the scalar. And it scatters the quasi-particles. That's the essential thing on mean field level. And now let's put these theoretical things aside and start with this interesting experiment that came up last year. The title simply tells what is proposed. You see, if you measure the Nernst effect, it's the Nernst coefficient essentially, which is the signal divided by field strength. And this is temperature, and you see different behavior for different data points here, 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 and here, which is different dopings. And in this material class, where you measure this in different doping beam, you have different tendency of stripe order. So in this area, you have no stripe order that you see by neutron scattering, for instance, whereas here at 1,8, there's very strong stripe order with a strong local moment of the spins essentially. And now how does this translate to this strange pattern of curves? Now, the essential thing is, if you look at this curve, which corresponds to a strong stripe order, you see two peak structures. And if you go away from the strong stripe order, here and here and here, these peak structures seem to merge and vanish, and there is no peak at all if there is no stripe order. Now, the interpretation is simply, this peak structure is very close, if you go down here, to the TC, and that's fluctuating superconductivity, producing this vortex Nernst signal. There seems to be another peak, of course, as I told, at 50 Kelvin, very much above TC here. TC is even more suppressed because this has strong magnetic fields to provide these curves here. And this means that this peak certainly has nothing to do with vortices, and is believed to originate from quasi-particles originating from a Fermi surface reconstruction caused by the strong stripe order. Obviously, there's some possibility to try to explain this structure by just a Fermi surface reconstruction due to stripe order.
When the Nernst signal goes negative, what does that mean?
Yeah, that's another important thing to tell. So this is at the boundary. You see this T mu is the temperature where this onset of this Nernst signal, which vanishes at this point. It's roughly equivalent to the point where the stripe order is not stable anymore.
Yeah.
And there you get a small negative and featureless signal. That's
I
usually
see,
what
it's always in the background.
that's what you observe when there's no broken symmetry and no fluctuating superconductivity.
But how do you define the sign at all? It's relative to
Oh yes.
what?
The convention is that the signal produced by vortices is defined to be positive, and this can only have a well-defined sign. If you define it to be positive, the whole Nernst effect sign is well-defined.
So it's defined always relative to the superconducting phase.
Yeah. Yeah.
But for instance, if I have just a normal metal in 2 dimensions for the spherical Fermi surface, I understand it's very small Nernst effect, but what is it, positive or negative?
You
If I have
reflect-
electrons, just, the simplest Fermi gas picture, is it plus or minus compared to this?
Well, the convention can be translated into some left-hand or right-hand system, essentially, I think, yeah. And this convention is such that if you have a vortex Nernst effect, you would have a positive signal.
I should be able to define
Isn't it sort of,
No,
you
it's-
share the attitude with normal Hall effect? That you basically see whether your carriers are electrons or holes?
But it's proportional to E squared. The Nernst effect is proportional to E squared. It doesn't matter.
Well, the signal can, for quantum particles, be both positive or negative, even if you define the vortex Nernst signal to be positive. So the quantum particles can change the sign. It does seemingly somehow here. Of course, this is difficult to tell. It's at low temperatures. But the vortices always have positive sign in this convention.
But I mean, what I'm asking is that you should be able to define Nernst effect without referring to vortices.
Yes.
Yeah,
So,
sure.
How you ask how it is defined. So
And you would think there's a definite sign to it.
you just, it's like the Hall effect. You define the gradient direction, you define the magnetic field direction, and you You find a positive signal along some specific field direction, which is usually a right-hand system.
It's like a negative or a positive voltage.
But the Hall effect is proportional to the charge. Here's proportional to charge squared.
Yeah.
So,
Well,
No, no.
to answer this question, hopefully the charge is not directly related to the sign of the noise
so
effect.
it's basically band structure.
It's band structure and band
Geometry.
masses and band velocities,
Yeah.
and
But your screen is.
hopefully it's just the screensaver. No,
Password,
who
password,
was the guy who had the
No more
password?
password
No
is
more
Alice, Alice with small letters.
I was supposed to hack this password?
Alice, Alice. I mean, it's the same as the. I mean, this was I borrowed the computer to another.
Yes, to tell us there's no relation of the charge sign to the sign of the noise signal, usually. Maybe there are some specific cases, and I come to these.
Oh, it's proportional to the transport entropy in the core, which is always positive. The
Yeah,
signal is
for-
proportional to the transport entropy in the core, which is
But when
positive.
you have just
So that's what pushes the
one-
vortex.
This is fine, but what I'm confused about is that, you know, in the normal state there are no vortices, there's no core,
Yeah.
but there's
No, I understand, but in the
So-
vortex state, it's well defined and it's always positive. Because thermal entropy is, sorry, the transport entropy is positive.
If the convention is that.
Yeah,
it's-
I
yeah.
imagine.
Yeah, and for quasi-particle there's nothing well defined for the sign.
So it has nothing to do with the sign, like in the whole.
So do you
have
add the
positive and negative.
quasi-particle or subtract it? When you calculate the contribution? Does it come with a minus or a plus?
My theory will only calculate the quasi-particle contribution, and that kind of positive, negative sign. You will see. It doesn't answer, you know.
No, what,
Uh,
it can be positive and negative depending what you do quasi-particles. There should be a rule there.
For instance, it can be the strike potential, which changes.
Yeah, so it's related to the Fermi surface shape or something.
Yes.
And then it's like when you have electron-like Fermi surface or hole-like Fermi surface, can you make statements about the Simons effect?
Not,
Look at gauge difference.
not like the fault connectivity. There's no rule when
There
the
should be.
area of the Fermi volume gives you the overall signal.
Yeah, there's no simple rule, but there should be a rule.
And the rule is not obvious to me, and there's no one else who can tell you.
No. I mean,
No, the rule is well.
for things that are microscopically fundamental, like the Peltier conductivity, there are definite rules.
You'll see.
I think the issue is that the Nernst coefficient is actually a product of the
Yes.
conductivity tensor and the inverse conductivity
It's a
tensor
very-
and the Peltier conductivity,
Yeah,
and that's
yeah,
why you
yeah,
can
yeah.
get
It's a highly
things going all
nonlinear
crazy.
object.
The Peltier conductivity is the really microscopically fundamental quantity.
So you do a raw measurement in a sense.
Yes.
We come to this point. It's a quantity consisting of several transport quantities, and these enter nonlinear, and that makes it difficult to relate to Fermi surface volume or anything else. That's how I'm going to calculate this signal. The system I assume is now covering the basic aspects of strike order. That's the scattering potentials, which scatter the quasi-particles. And on top of that, I just add the usual normal state dispersion on the square lattice, hopping with T prime, T double prime. And this captures the aspects of the broken translational symmetry. And the question is how this affects the Nernst effect of the quasi-particles. That's what I'm going to address.
So your stripes don't fluctuate.
It's assumed to be static, mean field,
Just
strike
static.
order, deep in the ordered phase at low temperatures. So essentially the coherence regime of this ordering pattern. And in this regime, you have quasi-particles in this model, and the transport is captured, believed to be captured by this Boltzmann equation, which is assuming realization time approximation. Essentially, I assume impurity scattering in this regime, which then can be treated in realization time approximation. And this is just very usual textbook-like transport. And now we come to the point how this Nernst signal relates to all these transport conditions. It's very clearly defined here. If you start from a linear response relation and you measure the proportionality between these currents and these two fields, thermal gradient and electrical fields, you have to say this is the heat current, this is the electrical current. You will have the thermoelectrical conductivity here, and by the Onsager relation, you have this conductivity times temperature here, and the electrical conductivity and the thermal conductivity are the remaining parts. And now you can solve this quantity in terms of this quantity times transport coefficient. In absence of charge current, you can do so, which is the boundary condition. And you get this expression for the y-x component, which assumes you have transverse field, longitudinal gradient. And you see all these quantities enter very nonlinear. And it's clearly, to me, not obvious how the Fermi surface enters into this overall quantity. It's clear for this particular quantity, and maybe also for some electrical quantities, but the whole combination is really not visible to me, how the Fermi surface affects this quantity. You have to calculate this from some...
Just because my ignorance, alpha y-x is the Peltier coefficient.
Yeah.
Yes.
Alpha is the Peltier
You can
conductivity
pulse.
tensor.
But in general, you have thermoelectric and thermomagnetic effects. So the thermoelectric effect generally exists without a magnetic field, like in a normal metal. And here, you pose, both thermomagnetic effects and thermoelectric effects, like Nernst effect. I mean, they should be separated somehow.
Yes, this is something to tell you. These quantities are assumed to be of zeros order in magnetic field, the electrical conductivities.
Oh, no, I'm talking about alpha. I mean, generally there are two types of thermoelectric effect. Thermoelectric effect and thermomagnetic
Yes,
effect. And
that's
one-
the next thing I would like to tell.
Right.
That simply these quantities are believed to, assumed to be proportional to magnetic field. You can do this in the sinusoidal shown.
So you ignore the conventional thermoelectric effect.
You expand essentially these coefficient of magnetic field strengths. You can do this systematically in Boltzmann.
No, I understand, but if B is zero, there is still thermoelectric effect, that's what I'm trying to say.
Certainly, I hope so.
So, and somehow you don't have it here. Is it there?
Well, you have some electric effect, but no off-diode one. So this one is, this is precedent B equals 0, whereas this is linear magnetic field. Because it requires a Lorentz force to be visible.
There's always a y-x there.
The Lorentz force has to be present to see this transverse response clearly. And this one is present at 0 field.
What if you had an anisotropic system and you weren't on one of the main axes? Then you would have something non-zero at zero magnetic field for alpha y-x, presumably.
Well,
I mean, that's not the case here.
We can always have
yeah, but when
in
it comes to
principle
Lorentz,
axis.
Right.
this will compensate actually. If there's no magnetic field, there's no spontaneous transverse signal. That's why I can overall define this Lorentz effect. Because it would be absent in zero magnetic field. Clearly, there's no Lorentz signal if there is nothing strange going on in the system. You would need to break some symmetries or time reversal symmetry or whatever, which I don't like to break here.
Also ignore Hall here then.
Cool.
You ignore Hall effect then. Something you have to.
Well, it's just this
It's all
quantity here.
It's all.
It's not when this is the Hall effect entering this quantity. I won't ignore that.
So you compute this, all these transport coefficients you compute by Boltzmann, given some Fermi surface.
Yes, I assume well-defined quasi-quantities, so I can resort to quasi-classical transport.
And it just makes a point that this Nernst signal is actually quite indirect, convoluted combination of the more fundamental.
Yeah, that makes it very logical. It will turn out to produce interesting effects once you combine all these quantities. There can be effects that are much more pronounced than for the individual components. That especially will turn out for anisotropic dispersions. Let me just come to this point. So, to start with, I now analyze the following case. I take this period 8 charge and spin order. This is a particular case where you set the described potential to some infinite value, which is dispersion less than the charge potential 0, and you assume the wave vector is 3/4 pi times pi. So this period, how is it? Period 8 in the spin sector, and this is period 2 if you are transverse. Now, And you see, first of all, of course, the Fermi surface changes its shape. And I look here at this particular potential strength, and how I analyze this potential strength is that it produces a particular local moment size, and you can compare this with experimental data. The maximum moment you see is 0.15 roughly in these materials, once you are very close by to 1/8 doping. And what you see is here are particular electron pockets. These are very small electron pockets. And once you change this potential strength, you essentially erase first these electron pockets, and then you form hole pockets here by fusing these open orbits. And now you ask how these changes translate into the Nernst signal. And first you see a strongly enhanced positive signal. First it's negative, so it can change sign. And that's just what's seen essentially in the experiment. If you, at this doping, you see very strong, not doping at this potential strength where you compare to the experimental local moment size, you see this signal strength, which is strongly enhanced and positive, comparable to experiment. And these are somewhat unrealistic potential strength. We would
I
have
find it all very unrealistic. I mean, there's this whole debate going on.
within
When you go into photomission, you can beautifully measure length bearing on this copper oxide, and there are supposed to be stripes there, and you just get to see your usual sort of Fermi arc business. Then there's Hassel-Alpha, seeing sort of small pockets. And now you're saying it's all tremendously sensitive to these Fermi surface details. These Fermi surfaces I haven't seen really either coming out from Hassel-Alpha nor on photomission.
Well, you can say the following. These Fermi surfaces have been proposed to explain.
They are theoretical constructs based on a completely oversimplified ideal.
How
These
far
stripes
this
are,
is developed.
I haven't seen
There's
them in
still
any
lots
Fermi.
of debate, of course.
Yes, there's lots of debate. Part of fundamentals, it was very clear how the Fermi
Yes.
surfaces and
I-
strike relate together.
We might also argue that this is very simplified. My claim is just I analyze what quasi-particles can produce, and if this is sufficient to explain anything, then I can't.
But the last thing I would take serious is noise effect, because it's so indirect, and it's just one number, depending on all these details you would like to measure directly. And you measure them directly in photomission or Hassel-Alpha, and you get to see something completely different. It's just very confusing.
Yes, I have to say I don't particularly concentrate on Fermi
Yeah,
surface.
it's likely not very important for us.
You just try to illustrate that the Fermi surface somehow. It's of course the cause that changes the signal, because the only thing that enters the signal is the dispersion of these quasi-particles. So I have to mention how the Fermi surface changes. And the essential thing is, once you want to have this positive signal, you have to have always these electron pockets, obviously.
Question.
In this regime.
Question. These
Yeah.
peaks, they appear when you have Fermi pockets disappearing?
You refer, for instance, to this?
Yes. And the
Yes.
anti-peak after that.
Yeah, it's very close by, and it's not the direct cause of the enhanced signal.
Okay, the reason I ask that is because in quantum Hall effect, you see peaks in Nernst effect whenever you deplete a Landau level. And
Yeah.
the reason you see that, and actually in an ideal, clean, three-dimensional
Yes,
system,
yes.
you can also see these peaks, but it's because of a Van Hove singularity in the density of states.
That's actually, you can read this up in one of my papers. Once you move to a Van Hove singularity, you essentially get some singularity in the signal. There's the fundamental function based on the fact that you can rewrite this derivative. Oh, it's essentially this one. All the thermoelectrical quantities are essentially derivatives of the electrical quantities with respect to the position of the Fermi surface, maybe times some temperature. And due to Van Hove singularities, this quantity is highly singular. If you plug
Be
this
careful
into-
for your laptop at the beginning.
I know the passwords. So you will see that these singularities essentially are related to such peak structures.
The bad news is that there's a sign of no singularities playing any role for photomission.
Yeah.
I mean, I guess, you know, the problem phenomenological question to ask is like, take these sort of whole pockets firmware arc pocket, suggested by photo emission to be related to the side face.
Yes.
And there are stories how you can get them. I have heard a whole lot of stories of people doing more complicated things than this. I'm getting it. Would that explain your word, Peach?
Well, I'm not sure whether I got the precise question actually. I'm sorry.
So, there's a whole big industry of people trying to relate what you actually see in experiment related to the firmware surface. The last thing you would like to do to figure out your firmware surface is an enhancement effect experiment. You do photo emission or an alpha that gives you direct information. There's now this whole industry of people doing way more convoluted, complicated modeling of the side faces to somehow tie together
Yes.
what you see in photo emission and what you seem to see in neutrals and so forth. And it's basically sort of aiming at, we want to see that you have these sort of pockets sitting there, that you have all over the place and like you see all the time. That are sometimes thought to be firmware arcs, and these kind of considerations always like the pocket.
Yes.
And you might have little sub-pockets and you have to know what happened. Severe was kind of obsessed about it. Now when you read in that information,
Yes.
could you explain a null signal? I just don't believe that these things make much sense, these firmware surfaces. They don't look like anything you've seen in a finished firm.
Well,
I know it can be done different.
but you can say the following. These electron pockets, if you look at these have been proposed to be these electron pockets seen in the quantum oscillations, at least the first.
Yeah, but these are tiny. That are not like these big pockets.
And
No way.
the size of these pockets, you have to divide it by 1/8, since the Brillon zone is not.
Right, so it's like on the one hand you have photo emission, on the other hand you have quantum oscillations. And somehow you have to reconcile these two sources of information such a consistent. And what comes out is like, yeah, we all believe in these pockets at the nodes, right, which turn into firmware arcs. And it might well be that there are little tiny pockets occurring in the antinodal regimes, right, and then they hit a subconductor or something and these things disappear.
Well,
Right, and you have only these small pockets in a large magnetic field. And that seems to be a consensus picture based on experiment, and really different from these firmware surfaces you use from here. And I've heard stories of people doing more fanciful stripes like pair-densitors and so forth, where you can kind of get this.
well, so far what is predicted that these electron pockets are seen in experiments.
No, they're not. What we see.
That's claimed by some people.
Yeah, I know, but Hasselhoff is very small electron pockets.
And this, the size of the pocket has also been fitted to the experiments by some potential strengths in this range. And however, these whole
I have
pockets.
heard now hundreds of stories about this. I don't think there's any, this is a very small minority vote in a big community of people.
It's one explanation of, I agree, it's more than these explanations being
Perhaps you should
available.
continue.
We should
So I would be the referee, I would kill this because,
This is not my work.
Sorry,
It's just, this has been proposed by different people.
So you're
I
talking
know,
about-
because they do this most simple minor potential. Come on.
So you're talking about
Many
quantum
others.
oscillations, specifically, when you said experiment, you're talking about quantum oscillation experiments or other experiments?
Yeah, quantum oscillation experiments were the first experiments to propose that.
That's so this is provincial attitude, that you have these
Uh-huh.
people who do transport, they only listen to Hasselhoff. There is this huge business with photo emission, completely ignored, and a couple of, sane people who say, oh, it's a kind of a puzzle.
But has it actually been done, photo emission and tight-airs material? It's tight-airs experiment, right?
Yeah, that's the problem.
This is
You
done.
can't do
There's, perhaps 20 papers out there that focus
On
on the
different materials.
stripes to all force. You get good photo emission signals. And the mystery is that these stripes, when you're studying, doesn't seem to change anything about the photo emission signal. You see the same frameworks, the same whole pocket sitting at the nodal positions and so forth.
Well, it's in these materials that the stripe are not clear whether the quantum oscillation experiments will tell something, since there are no quantum oscillation experiments. That's why it's in these materials not clear whether these pockets are even observable, since there are no experiments.
I mean, I'm basically arguing that you cannot have a story that's really relying on the deep details of the event subjects. I can always say there are some generic features, perhaps like I need electron-like pockets, right?
I
And
wouldn't
apart
say
from that,
that
that's sort of fine.
all that is quantitatively correctly explaining anything. You will renormalize these dispersions by interactions. I'm just heading towards the generic features of the Fermi surface and the overall sign of the signal, and not on the quantitative agreement with any experiments. So now another feature, not quantitative but qualitative, you see the doping dependency of this signal, which is, well, first of all, modeled by the doping dependency of stripe order, and this is a mean field dependency, somehow, of course, consistent with all this mean field calculation. You have this exponent of a square root dependency, and what you see if you dope the material from this value, which is the critical doping for the onset of stripe order, you move into this 1/8 doping continuously, and you see this positively enhanced signal. That's not quantitatively, as I like to tell you, agreeing, but qualitatively it's quite the same. Quantitatively you have to, of course, fit something, and it's not clear how to fit this precisely. It's just constant fixation time. So this I won't like to explain in detail. Now, the same thing you can do for the temperature dependency of this signal, and you once more see this mean field dependency on the temperature with the particular onset temperature of spin stripe order, which is roughly this range, 50 Kelvin. And what's seen here is the same than what we saw in this experiment. The signal turns negative here. Due to the onset of stripe order, turns strongly positive, and gets this linear behavior due to the Fermi liquid regime of this model. And this is qualitatively the same that we saw in these experiments. You can play the game for different periods, and that's what I'm trying to distinguish from this period 8 order. Now, if you take a period 10, which would be at some underdoped range of this material, you will see a very different structure. And you can relate the structure to the electron pockets and hole pockets in this case. You will see that here there are only electron pockets in the Fermi surface, and how the signal turns negative once you have also only hole pockets. And so, in fact, this kind of pattern would not agree with any of those experimental details. That's why I'm showing this. And to conclude this, or what I like to conclude out of my calculation, that this Fermi surface reconstruction seems to be indeed in agreement qualitatively with this enhanced Nernst signal, and also this calculation suggests that some sign changes can occur in the Nernst signal if you go to the underdoped region, where you have higher periods of the stripe patterns like this period 10 I showed you. So this calls for some experiments, of course, in the underdoped region to possibly detect sign changes or other features of this Nernst effect, if you'd like to agree with this quasi-particle picture I present you. And
I guess there's a sense that in order to get a big Nernst effect,
yes,
you better have relatively small pockets. Is that the first step?
That's not a clear statement. The size of the pockets is not related to this amplitude or the design of the signal. That's not.
There should be a qualitative logic, otherwise I don't know what to do.
I think you, just from the, and this is called the Mott formula, what you want is a big derivative in the density of states.
If there's a singularity, that's large.
Yes, but sure. But I think if you have a smaller Fermi pocket, that derivative will be larger.
It will depend also on the curvature.
Oh, sure.
How far this ranges with the
Yeah, when the pocket emerges, you have a
So experimentally, I haven't seen any sign of with different house singularities or anything sitting at low energy, except when you go above T star, there's a real sense of singularity.
Well, in fact, we will come to this point. In the qubits, then essentially there is a Van Allen singularity.
I know, but you look at photon emission, there's this beautiful story recently by CXM that you actually recover this silly LDA van hoofdsingulariteit en de nodes when you are above T star.
Yes.
Then below T star, all stars are equal completely
Yes.
in the pseudogap area.
Yes, yes.
And I don't think that the temperatures, that this baseline temperature is smaller than the pseudogap. And therefore the pseudogap stuff is very complicated. It's not quite contributing to the transport. It's all associated with another region. And you believe photoemission.
Yes.
And that is like these, you know, pretty nice G-wave non-thermal type things there.
Yeah, I come to this point. We will illuminate this further. It's really important.
Sorry, but isn't it correct to say that to get an Ernst effect, you need to break time reversal and particle Hall symmetry in some sense?
Well, you break the time reversal by the magnetic fields.
For instance, if you have perfectly particle Hall symmetric system, which a Fermi gas actually eats, you will in fact get a zero Ernst
The
effect.
question of particle Hall symmetry. Well, it's
And
not a
if
flow
you
that's
deform the
always
Fermi
goes,
surface, which is pretty much breaking particle Hall, then you will start generating
No, the Nernst effect exists for parabolic band.
in not in two dimensions. If you look at the Zonheimer formula in 1949, which is the formula to actually calculate the Nernst effect, it's proportional exactly to the derivative of the
Right, yeah.
of the
Yeah.
density of states,
Yeah.
which in two dimensions is zero.
If you have a simply connected Fermi surface, which is spherical, this cancels. That's true. But it's not a particle symmetry case in principle. If it needs just to be spherical, and I'm not sure whether particle symmetry will cancel the signal. I'm not sure because I only look at the doped range. I would tend to say it's not cancelled.
No, it's enough to think about the analog of a quantum Hall of a classical Hall effect for electrons and holes. If you put a temperature gradient, the particles, regardless of their charge, move from the hot end to the cold end. In the magnetic field, the electrons and holes get diverted in opposite directions.
Well, intuitively, I came now up with the idea that so if you look at the formula, I mean, this is not very important, but just to kill these questions, it's now it works like that: sigma xy, alpha xx. So sigma xy is zero particle symmetry case. We can ignore that. So there's alpha xy, sigma xx. Now alpha xy is the derivative of that quantity, so which is zero. That's also zero. So we can kill that. So the overall quantity should be zero. That's I think should be zero due to this argument. But to be sure, I should check this. I didn't look at this because there's no particle symmetry in this system. Which I'm looking at, it's always doped.
Yeah, but that's the microscopic particle symmetry. Right? Here it's really about the Fermi surface particle symmetry. Your argument, the two-dimensional parabolic band is effectively particle symmetry. That is about the density of states, so completely independent of everything. There's no difference between faster particles and quasi-holes.
You can get some effect due to the bottom of the band, but it's
Yeah.
going to be
But
potentially small
yeah,
and
but temperatures have to
inferior.
be that high that you see it.
Yeah. Well, it's not of importance to the part of the phase diagram. I believe really. So that's an important point. Now we come to the fact whether the Coop-rate pseudogap phase is related to this quasi-particle Nernst signal I was heading at. And it will be if I assume rotational symmetry breaking is playing a dominant role along this transition. And why I'm talking about this is, well, first, this was the first experiment that discussed this really in some believable manner. Here you see the spin fluctuation spectrum. It's actually kx and ky direction in a particular region, which is not some symmetry center. It's at least anisotropic, and that tells us there is a broken rotational symmetry. And this has been called electron liquid crystal state, not by these people, but by Steve Kibbleson some years ago, before this experiment has been performed. And there has been a long...
Shouldn't you say Eduardo Fredkin is Eduardo is more obsessive about it?
First name, I just naive. His first name is not alphabetically ordered, so these are all the authors, at least, who contribute to this. And it has been a long-standing question how this phenomenon of rotational symmetry breaking is situated in this pseudogap phase. It's just measured somewhere here, roughly 150 Kelvin, but it has not been clear whether this onset, the pseudo gap, is related to that, or if below this temperature you see the same. And because we have this superconducting dome on top of that and all these problems. Now, there was this very well considered to be spectacular experiment by several people, where now the measurement of the Nernst signal, of the quasi-particle Nernst signal, gave some new important insight. Now, the essential thing is, you look here at the A components, so take the unit cell and define this to be the A direction, this is the B direction. And so you see here the thermal gradient in A direction, transverse component Y direction of the signal, and here you see the B direction of the thermal gradient and the transverse field in the opposite direction. And you see the size of the signal for all these dopings seems to be 1 order of magnitude different. So it's a factor of 10 anisotropy of the signal, which is very spectacular if you consider the conductivity, which is very much less anisotropic. And it's very much less clear whether it's a nematic phase or just the copper oxygen chains, which produce this anisotropy. And doping, where this is most pronounced, is, well, it's strange the color size changed here. It's close to 1/8 doping, essentially. And close to 1/8 doping also means strong tendency to increments with spin fluctuations. Now, more spectacular, even, is the fact that if you take the temperature where this anisotropy sets in and plot it here, so it's these red, green, blue, whatever points, it somehow is nicely interpolated by the T-star line of the pseudogap phase, which is quite another quantity by definition. But it seems to be somehow coinciding, as far as the experiment can tell us at least. The error bars somehow fit on this T-star line to the pseudogap phase. So what this tells us is simply summarized in this sentence. The pseudogap phase tends to be a broken rotational symmetry phase according to these measurements. So what Steve Gibbelson and Fredkin and all these people like to have, namely a nematic phase and a pseudogap phase, seems to be realized in, according to these measurements. And that's, well, very important to understand.
I have a quick question. What direction does these pneumatic mean? It has to choose a direction, right?
Yes.
So why would the pneumatic phase just break up into little, randomly oriented things? Why does it choose to take
This
domain.
was 2 on 4.
Yeah, this is the following argument. There's the copper oxygen chains,
This is 1, 2, 3, right?
which should provide an effective field coupling to the nematic order.
So there's 2 directions.
No. No, the issue is that this is in an orthorhombic crystal where A and B directions are different because the
Yeah.
crystals are just different.
It's also
So in this way you can have take as an absolute proof
Yeah.
for spontaneous symmetry break, but then the argument is you have these enormously large effects, actually also neutron scattering, and it's sort of hard to see how it can just come from chains.
Yeah, but it's also
And then
twin.
it
That's why we
amplifies
see
sort
all
of
crystal.
this lattice symmetry breaking gets amplified in an atomic
So it's like a-
system because it's like beaming. the
So-
It's like an
nematic
Ising
domains.
transition in a field.
Yes.
So,
This thing is really sharp.
but there's some sort of bias from the lattice itself. So,
Yeah.
and that's all you need to get things aligned.
Icing in the field, exactly.
But Professor, I saw that one of some other people mentioned try to reconcile the output data by proposing, let's say, Jacquard.
It's the in the LTT
From layer to
phase.
layers.
Yeah, that is different.
They alternating
Yeah.
the orientation.
Let me tell
Yeah,
you.
I'd like to get
It's,
into
it's,
this.
there is
Some collection
some
items.
clear arguments, the following. These materials, the YVZO family, they have these copper oxygen chains, and also they have a distorted unit cell by its own. And this, in principle, breaks the symmetry already before you can break it by any nematic order, so there's no sharp transition, therefore, to the nematically ordered state. However, you can observe nematic order due to the fact we have this pre-broken symmetry. It can define as well defines the direction of the order. In other materials where you have no anisotropy, like titanium, bronze, and copper oxide, you can see this nematic ordering transitions. It's simply there's no broken symmetry beforehand, and there's no preferred direction where the nematic order can point to.
So was the crystal twin?
This is the twin at that.
I think
This is all these twins.
Twins.
Part of the secret. Examples are hard to get. You see it, right? It's just both hard masses of these twins.
Yeah.
But from your point of view, when you calculate the Nernst, all you need is to fold the Fermi surface, right? So basically, it doesn't really matter from your point of view how you break the symmetry. You just need the fact that it's broken, right? So how can you distinguish pneumatic from
Next slide.
The next slide is coming.
Uh,
Yeah, so one more remark. I mean, this is about sort of the political correctness, and pneumatics are right now politically correct. When this data would have been presented 5 years ago, people would have said, oh, we see the transport along chains. And now you can, of course, argue that's not very likely, but it's always, I mean, officially, it's nervous. There's one example which is not nervous, and that is the St. Andrews quantum critical ruthenate. This is metamagnetic transition, where you have basically tetragonal whatever crystal, and they really find spontaneous transport anisotropy.
Yes.
Right? And as I see the
He
official
really
statement.
claims that people constructed some measurement procedure where you can exclude that the chains produce this anisotropy.
Yeah, but then you can always
I don't
negotiate. You
understand.
can always negotiate.
I can understand these arguments, but
Yeah.
the basic argument
No, you can always negotiate. It's really about the mood of a
the
community.
ratio is a factor of 10. And that's the argument. It's very strong. It's not the factor of 2.
I'm a cynical old fart, you know.
It's not conclusive to
I just know how important the mood of a community is.
It's a proposal I like to illuminate further. That's my
I see.
standpoint.
There's some disclaimers and warnings. 5 years from now, pneumatics are out of fashion.
Yeah. I'm just repeating what has been proposed. I am not necessarily agreeing with anything. The point to explain anything that comes now. Now, the first question has been, why is there no other sorts of anisotropy that can explain this anisotropic signal? One thing might be stripe order, which has a preferred orientation and therefore breaks also rotational symmetry. Now I can just take my old calculations and see whether the anisotropy is that large or not. And I take this typical case, all the other cases look similar in terms of the ratio of anisotropy. You see here xy component, yx component, that's just celebrating x and then y direction in this case. And if you divide these numbers, you see it's smaller or equal to, if you're not in this extreme limit, or it's maybe 3. And the ratio in experiment is simply 8 or 10. So my argument is this is not enough to give this strong anisotropic signal. Moreover, I will find a reason why, when it can be very strongly anisotropic, so I ignore this case basically. And now the case I like to look at is, of course, the real electron nematic order, which is nicely proposed by Steve Gibbelson and other people. And now I take the case, of course, of the simple quasi-particle picture. And this is quite clear in the sense that nematic order couples to the band structure, and very basic effects should already be seen in the quasi-particles. And in this case, I looked at some dx squared minus y squared distortion. This is believed to be precursors, broken symmetry of the stripe phase. That's simply produced like that. You simply distort the xy hoppings by opposite sign, coupling to some scalar order parameter. This nearest neighbor hopping is 1, next nearest neighbor, no, next nearest neighbor hopping 3. And this simply is describing the linear coupling to the order parameter, which is the anisotropy ratio essentially, and of this nematic order. And what this does, it breaks the C4 symmetry down to C2 symmetry.
Yeah. So we are comparing now that you should call this tetragonal to orthorhombic. C4 to C2 sounds too interesting.
I like to use brief symbols. I mean, you can call this whatever you want. You cannot,
No. It's all politics.
Well, you're a politician, I was.
No, I'm not. this thing is political. Started by Seamus States. We tried to make it unpolitical. This is just tetragonal to orthorhombic. Sounds very old-fashioned, and that's what it is.
Well, we'll vote for you.
I'm not alone. I mean, it's basically, I have my stakes in these liquid crystals, but there's sort of getting too fashionable, and it's, people use too nice words. Has to be with the fetal.
No, we have at least two possible explanations of this.
Yes, there's two explanations.
Which are mathematically identical, so I'm still satisfied.
Just giving you advice.
And now, just calculate this and do it in the following way. To subtract both components, normalize it by the mean of both, which is defined to be this object, and take the derivative with respect to this order parameter, which is therefore the susceptibility of the anisotropy to this order parameter of the nematic distortion. And this is color-coded here, and where it's white, there's simply no filling, because I plot the chemical potential in this range. The bandwidth is 4 exactly, -4 to +4 in units of T1. And there's no filling just here. And what you see here is essentially this Van Hoven singularity I refer to. This is at mu over T equal some constant, I think. Yeah. At this Van Hoven singularity, you see a strong enhancement of this anisotropy, interestingly. It's not, as you argued, essentially, it's not part of the phase diagram of the cuprates, essentially. You will nowhere directly find this Van Hoven singularity, except you dope to some extreme limit where it's not feasible. So I'm rather in the physical real material, I'm rather in this area where you have this ratio of about 5 or 4. Not about 5 or 4. It's simply much stronger than the distortion of the band structure. The response is 5 or 4-fold stronger than that of the kinetic energy. This tells simply the response of the non-signal to anisotropy is very much amplified to any kinetic energy changes. This can be rephrased more precise if you look at the anisotropy as a function of this parameter.
I assume scattering to be isotropic in the model.
Yes, I assume.
Well, that's strange, right? Because scattering obviously should be
That's a following argument. This distortion does the following. It's basically starts from here. Now it distorts, looks somewhat like that in the extreme case where you have open orbits. And if you look at scattering, the only thing that could spoil this calculation of the scattering here and here is very much different. That's my point. And I think the cuprates, these points, it's not like antinodal and nodal region, it's opposite points.
The nodes and are the antinodes?
This is the nodal line, right? And this is the.
Right, so again, at the antinodes, you see these very big.
I mean, the nodal line is here. It's not at these points where the distortion really works.
But again, we have the information about from photoemission, and we just know that the antinodes, you have these big pseudo gaps in this regime where these things happen. So how to relate it to anything in your computer?
What my argument is
If you don't forget arc,
that the points where the anisotropy of the band structure occurs are not equivalent to the points where the anisotropy of the scattering rate in the scope rates is believed to work. That's my argument. It is quite clear that the nodal line is here, whereas the nematic distortion operates here and here, basically.
All the time the same column. I would like to see a relationship between the observed electronic dispersion Fermi surface and so forth in RFS and anything you compute. And that Fermi surface is not observed.
is not observed because the only thing where you have observed something is the Nernst effect.
Let me ask you how much do you have left? So just to make time.
This is many questions. I can.
Perhaps it should
It's only 2
simply
slides.
let you talk and
Oh, yeah.
bring it to an end.
It's 2 slides. I
Yeah.
make it short. So you see basically this y-x and y components are very much different. Even can reach an infinite ratio to zero crossing, which is not possible for the connectivity, which has only respect of 2. You see also in experiments. That's my basic claim. And I can summarize this in total. Now we are really done. What I showed you is that the quasi-particle Nernst effect is strongly enhanced by stripe order. And the second thing to tell is that the Nernst signal is seemingly a good tool, quite unique even, to detect pro-connotation symmetries. And that suggests also to look at such materials and measure the Nernst effects and see whether my
It has
proposals
to be
work.
done, yes.
And if it has been done, I'm not so
I don't think it has been done.
that would be good. I should see this. And the next thing is, well, my results somehow strengthen the proposal, at least, that the two-wave phase is really a magnetically ordered state. And that's quite a strong thing to tell, and maybe you will not strongly agree with that overall.
No,
But it seems like this really is a perk. Yeah, so far it's everything I have to tell.
Thank you very much. Usually many questions. So any more questions?
one more thing. I mean, I'm basically neutral in this whole business. When it's true, it's great. Now there's kind of a shift, I think, in the mood in the community again. So there are these many other proposals for what the symmetry is in pseudocap phase, where the strongest contender is these orbital current style John Pharma.
Yes.
Right? Now there was this meeting in Shanghai, the big one, the SNS meeting, and Ushida decided, and he gave the conference summaries, and we both scored basically on this point, that the sort of news at this meeting was that finally these different tribes having different paths, explanation for in an order, have started to accept that everybody's actually doing good experiments, and that actually all these things are going on at the same time. Right? So there's cyclic things, pneumatic things, before pair things, orbital current things, there was a lot of support for it in the meantime. And there was this beautiful story coming from Paris where also the orbital currents have been detected now in stripy 204 in the form of diffuse scattering, so it lives together somehow. Now what I found actually perhaps the most interesting thing happening there is that John Farber at the point put up his finger and said, I can explain this Taillefer signal based merely on the time reversal symmetry breaking of my orbital current phase. Have you seen that?
Yeah, I've seen that because your colleague at Leiden, Karl Wehnacker, came to me why I wrote this strange paper. He insulted me that I wrote this paper, which you refer to.
That was Pharma and
and because he doesn't believe it, because it would tell that Onsager's relations are broken in the cuprates.
I saw that they were resting on Onsager.
They say that's violated due to the fact that these measurements tell you that there's a strong anisotropy, and they cannot tell why this should be produced if Onsager's relation is valid. And that's opposite of what I'm telling you. So I cannot tell you why these people write something in this direction, because I can tell the
We can have looked together at it. I'm really confused.
I don't believe this paper, because my explanation works also without breaking Onsager's relation. So I don't
confused. I thought they were just doing Onsager.
Yeah, it's definitely I read this
Basically
paper.
saying that when you break time reversal and it's very complicated, it can end up in a way as if
You should read this paper. It's opposite to my proposal, and therefore this.
But
yeah.
again, going back to what quantities are fundamental and which are not, Nernst is not. It's this mixture of electrical conductivity and thermoelectric conductivity And Onsager's relations all talk about the fundamental transport coefficients, Peltier, and electrical conductivity. Could this, I mean, the Onsager relations tell you something just about the symmetry of these various tensors,
Yes.
that the symmetric part is odd in magnetic field and the symmetric part is even in magnetic field. And if you have, say, a significant variation in the symmetric part, that's even
enough.
in magnetic
That's
field,
enough.
that could
That's enough.
screw things up in Nernst effect, and if you're naive about the sources of different
Yeah.
things, you could fool yourself.
Yeah, that's
into
why I
thinking.
believe the non-sider relations need not be broken if the
Yeah.
signal's anisotropic. As I argue in this whole talk, this
Mhm.
paper just tells the opposite, so I'm not aware why this paper should be true in any sense.
I know John Farmer very well, and I cannot imagine that he claims that Onsager got it wrong.
It's even not
Yeah.
well, it's called
Maybe-
probable violation of Onsager's relation, but the only content of the paper is to argue why it's violated. Probably. So
This is a preprint that appeared a few
it's a
weeks ago.
three-page
Yes.
preprint.
Yes. I have it in my computer.
You can discuss.
I want to understand it better.
Yeah.
Who is it by?
Warmer and then Kapitolnik and some other.
No, is it Kovchenko?
Yeah,
Guy from
it's-
Maryland,
yeah.
who's also doing
Yakovenko. Yakovenko.
Yakovenko, Kovchenko, Yakovenko, exactly.
Yeah, maybe we can discuss this. It's really time to.
Yeah, we have to.
But,